Welcome back, and thanks for being here. On this channel, we start with real science, follow the evidence, and explore the mysteries that still don't have answers. If that's your kind of story, like, subscribe, and turn on notifications. Now, let's get into it. From the moment it enters the shared databases of sky surveys, the object that will be called 3I Atlas appears routine. Automated software flags a faint moving point against the fixed stars, one more icy body drifting through the inner reaches of the solar system. Observers classify it the way they classify thousands of such visitors, as a probable comet with a hazy envelope of material beginning to bloom around a frozen core. The first notices list a path, a changing brightness, a likely orbit. Nothing in those early estimates suggests that this traveler does not belong. Yet when astronomers fit a path to the new object, the best solution is an open track, a hyperbolic arc that does not close back on itself. The trajectory does not curve in the way that ordinary comets do, those long-period wanderers bound to the sun by ancient gravitational ties. This means the object is not simply falling in from some distant reservoir of ice far beyond the planets. It comes from outside, from interstellar space, crossing the planetary system once, and then leaving again. The designation changes to reflect this status as the third known interstellar visitor, and as a discovery credited to the Atlas survey. But the label still carries the assumption that this is an icy body shedding gas under the light of the sun. It remains natural to believe that 3I Atlas is a comet until the evidence demands otherwise. Telescopes turn toward it from Earth and from orbit. Robotic observatories that map the sky in broad sweeps add new points to its growing record, while larger instruments follow with deeper looks, resolving a faint halo known as the coma, the luminous cloud of gas and dust that surrounds a sunlit nucleus. The picture remains familiar. The coma brightens as the object approaches perihelion, the point of closest approach to the sun, just as ordinary comets do when sunlight strikes more intensely and buried ice begins to sublimate. Tiny changes in brightness from night to night reveal how quickly material escapes the surface. Subtle shifts in the shape of the coma suggest jets, narrow outflows that mark regions where sunlight reaches deeper layers of volatile ice. Teams repeat familiar calculations, comparing energy from the sun to the rate at which ice can turn to gas and drag dust along with it. Everything about this stage could, in principle, belong to a normal comet, and for a time, the community treats it that way. Observers expect a tail to grow in the usual direction, swept away from the sun by the solar wind and by the steady pressure of light itself. A curve of material streaming outward, part dust, part charged gas, a pattern tested many times in both observation and simulation. Even so, small mismatches resist easy dismissal. The relative strength of the halo, compared with the faint beginnings of a tail, seems unusual, as if the material around the nucleus is thicker and more confined than expected for a natural outgassing process. The spread of dust does not fan out exactly as predicted by simple models. When astronomers look more closely at the direction of the emerging structure, the geometry is not entirely comfortable. Measurements hint at material that does not flow neatly away from the sun. It is too early to describe this as an anti-tail, but the seeds of that description are already present in the data. As the weeks pass, the object moves along its path, falling inward, swinging around the sun, and starting its climb back toward the outer regions. The interstellar origin is now widely accepted. The slight excess above escape velocity fits with an object that has crossed interstellar space and is only briefly passing through the gravitational well of the sun. This alone makes 3I Atlas rare. It joins a tiny family of known visitors from beyond the planetary system, each one a sample of conditions in another stellar environment. For many scientists, that status would be enough to justify intense scrutiny, and survey teams coordinate to watch the object through perihelion and beyond. Space-based observatories, freed from the blurring of Earth's air, begin to return more detailed images. Among them are snapshots from the Hubble Space Telescope, taken in campaigns that balance limited observing time against the opportunity to watch an interstellar object evolve near the sun. These images undergo specialized processing designed to tease out faint structures, revealing jets and tails that would otherwise vanish into the glare of the coma. The patterns that begin to emerge are not entirely comfortable fits to the standard comet picture. At the same time, the James Webb Space Telescope turns its gaze toward the object in certain windows of its schedule. This observatory does not merely take pictures. It spreads light into spectra that record the fingerprints of molecules. In those early spectra, scientists see the marks of common volatiles, including carbon dioxide, the same gas that drives outbursts in mini icy bodies when sunlight reaches buried layers. On paper, this seems reassuring. A body with carbon dioxide-driven jets sounds like a comet. Still, there is a mismatch between the distances at which this gas is detected and the distance at which normal sublimation should operate efficiently. The discrepancy is small at first, easy to attribute to uncertainties in the models or to imperfect knowledge of the object's exact size and composition. But it does not go away. In its first months under watch, 3I Atlas takes shape in the collective mind of the astronomical community as a paradox. It is both familiar and strange. It brightens like a comet, sheds gas and dust like a comet, and yet travels on a path that marks it as an exile from another system. It bears the chemical signature of a volatile-rich body, and yet hints at structures that do not fully match the physics that every cometary model assumes. The story is still in its quiet beginning, but the pieces of a deeper puzzle are already laid out. Later, the words antitail and triple jet will dominate discussions of this object. For now, there is only a sense that this interstellar visitor is holding something back, that the most important aspects of its nature still wait behind the first layer of data, just beyond the reach of easy explanation. In order to understand why 3I Atlas becomes so troubling to established ideas, it helps to step back and consider how ordinary comets behave under the sun. A typical comet is a frozen remnant from the early days of a planetary system, a mixture of rock, dust, and volatile substances such as water ice and carbon dioxide ice locked together in a fragile nucleus. For most of its long journey around a star, this nucleus is inert and dark, turning slowly in deep cold. When such a body falls inward and sunlight gains strength, the outer layers begin to warm. Ice buried just beneath the surface turns directly from solid to gas in a process called sublimation. The gas escapes through cracks, vents, and porous layers, dragging loose dust with it into space. Around the nucleus, this stream of gas and dust builds a hazy envelope known as the coma. Under a telescope, the coma appears as a soft sphere of light, its shape a blend of motion, pressure, and radiation. The sun's heat provides the energy, and the escaping gas carries material outward in all directions, but the larger forces of the space environment then take over and impose order. In the inner reaches of a planetary system, two main influences shape the material leaving a comet. The first is the solar wind, a continuous flow of charged particles that streams outward from the star at hundreds of kilometers per second. The second is the radiation pressure of sunlight itself, the gentle but persistent push of photons on small particles. Gas atoms and molecules that become ionized, meaning they lose or gain electrons and carry electric charge, respond strongly to the solar wind and to the magnetic field embedded within it. These charged particles are swept rapidly away from the sun, forming what is called the ion tail. This tail tends to be narrow, straight, and aligned almost directly opposite the sun, like a luminous ray pointing away from the star. The dust grains, larger and less responsive to magnetic fields, feel the steady push of light more than the pull of the solar wind. Their path is shaped by a balance of gravity and radiation pressure, and the dust tail often appears broader and gently curved, tracing a path that reflects the comet's motion along its orbit. In images of well-studied comets, these two tails can be separated by their structure and by their spectral signatures, with the gas revealing characteristic emission features and the dust reflecting sunlight in a smoother continuum. Jets add further richness to this picture. A comet's surface is irregular, and not every region receives sunlight in the same way. Localized patches of volatile rich material can erupt when their local dawn arrives, sending narrow streams of gas and dust sweeping off the surface. As the nucleus rotates, these jets can trace out spiral patterns in the coma, or produce fan-like structures when viewed at certain angles. Researchers have observed such behavior in many comets and have built a frame of thinking in which rotation, heating, and uneven surface composition naturally give rise to complex but understandable patterns. When the comet's rotation axis is tilted relative to the direction of the sun, different regions come into and out of illumination during a single spin, and the jets flicker and shift accordingly. Over hours, the length of a jet can change as well, depending on the rate at which gas is produced and on how quickly it is dispersed or swept away. Typical gas velocities from sublimation processes are a few hundred meters per second for carbon dioxide-rich outflows, rising and falling with temperature and composition. One more category of feature plays a role in the story of 3I Atlas, and that is the phenomenon called an antitail. Despite the name, an antitail does not literally point toward the sun in the way that a jet of gas might. Instead, it arises from projection effects, when an observer's line of sight aligns with a plane of dust particles left behind in the comet's orbit. As the comet moves, slow dust grains can lag along its path. When Earth and the comet occupy a particular relative geometry, this sheet of dust can appear as a spike extending roughly sunward, even though each grain follows a more complicated orbit. Antitails of this kind have been documented for several comets in the past. They require a specific combination of orbital positions and ejection histories, but they remain consistent with the same underlying physics of dust and light. Even in such cases, the antitail is usually a secondary feature, weaker than the main dust tail, and limited in extent by the finite time during which the geometry is favorable. The gas behavior still follows the pattern of being repelled away from the sun by the solar wind. From this perspective, cometary science rests on a coherent narrative. The sun heats the nucleus, ice sublimates, jets form, dust and gas flow outward, and the environment sculpts these flows into the familiar components of Comet, tails, and occasional projection-driven antitails. Observations of many different comets have strengthened this picture. Instruments on missions such as Rosetta, which orbited a comet and watched its surface up close, have directly measured gas speeds, dust grain properties, and the interaction with the solar wind. Ground-based and space-based studies have mapped the evolution of tails over time, relating changes in shape and brightness to physical parameters of sublimation and rotation. When models are tuned with reasonable assumptions about composition and nucleus size, they reproduce the broad features of what telescopes see. This success builds confidence that, although each comet has its own personality, they play variations on a shared physical theme, rather than inventing new rules each time. It is against this carefully built background that 3I Atlas must be measured. When Hubble images processed with rotation gradient filters begin to reveal a prominent structure extending in the direction of the sun, the term antitail rises naturally to mind. Yet, this is not the subtle projection feature that older examples have taught astronomers to expect. The sunward structure associated with 3I Atlas is long, bright, and sharply defined. And in certain images, it dominates over the conventional tail that should be carried away by the solar wind. On even larger scales, the antitail appears more extensive than the outflow in the anti-sunward direction, reversing the usual pattern. At the same time, on smaller scales closer to the nucleus, 3 distinct jets emerge, arranged with an almost equal angular separation around the central point. One of these features points roughly away from the sun, while the other 2 lie to either side, forming a sort of 3-spoke pattern within a halo only tens of thousands of kilometers across. The outer structure and the inner jets together form a composition that feels uncomfortably organized when set next to the expectations born of ordinary cometary physics. The instincts of scientists trained on many natural examples are to search first for conventional explanations. Perhaps the antitail is still a projection effect, exaggerated by unusual viewing geometry. Perhaps the jets simply happen to originate from 3 active patches that lie at similar longitudes on a rotating body. Perhaps the apparent symmetry is partly an artifact of image processing techniques that enhance certain gradients more strongly than others. Each of these options remains worth exploring, and models are adjusted to see how far conventional physics can be stretched to cover the observed patterns. But as more images accumulate, and as spectra from James Webb and other instruments continue to trace gas and dust along the sunward structure, it becomes clear that 3I Atlas is pressing against the edges of the usual comet framework. It behaves as if it acknowledges the standard rules, then quietly bends them, producing an antitail that looks less like a quirk of viewing angle and more like a persistent, directed feature. One that calls for a deeper examination of how far sublimation and radiation alone can go in sculpting matter around an interstellar visitor. In the weeks after perihelion, when 3I Atlas has swung through its closest approach to the sun and begun to recede, the most striking feature it presents to distant watchers is not the behavior that most comets display, but something that appears to run in the opposite direction. In processed images from the Hubble Space Telescope, the object displays a long, narrow structure extending toward the sun, a sunward plume that strains the comfortable language of ordinary comet science. On the largest scales that these images resolve, out to roughly 100,000 kilometers from the nucleus, this sunward feature stands out more clearly than any tail carried away from the sun. The structure is slender compared with its length, as if confined within a tight corridor rather than spilling broadly into space. When rotation gradient filters and other enhancement techniques are applied, the contrast sharpens. The anti-tail, as observers begin to call it, is not a faint trick of perspective hiding among brighter, more familiar features. It is the dominant expression of activity around this interstellar object, a statement written back toward the star it is leaving behind. To understand why this matters, it is important to recall that the solar wind and radiation pressure both push material away from the sun. Dust grains, once freed from the nucleus, move under gravity and the steady push of light, tending to form curved streams roughly opposite the sun. Gas that has been ionized couples tightly to the magnetic field and the particle flow in the solar wind, racing away at hundreds of kilometers per second. The idea that a persistent, collimated structure can extend toward the sun for tens of thousands of kilometers challenges this pattern. In ordinary projection-driven antitails, the apparent sunward extension is really a sheet of dust lying near the orbital plane, seen from a privileged viewing angle. The material itself is not streaming toward the sun. It simply sits in a configuration that, when projected onto the sky, mimics a tail pointing back at the star. Such features are transient, dependent on the particular alignment between comet, sun, and observer. They do not usually exceed in prominence the main dust tail, and they do not involve gas streaming sunward over vast distances, because gas is quickly seized and swept away by the solar wind. As images of 3I Atlas are taken at different times, the antitail refuses to behave like a temporary alignment trick. Comparisons between snapshots taken late in the year, separated by nearly a month, show the sunward structure remaining strong and coherent while the object moves along its path. One set of data is processed to highlight scales of about 100,000 kilometers, in which the antitail dominates the entire scene, a bright lance heading sunward, while any anti-sunward tail appears comparatively subdued. Another set zooms into a region roughly 24,000 kilometers across, showing the inner profile of the outflow near the nucleus. At this smaller scale, the antitail still asserts itself as a dense, central spine of material around which other structures arrange themselves. The persistence of this shape over time indicates that whatever drives it is not a fleeting outburst or a passing geometric coincidence. It reflects an ongoing, organized process anchored to the nucleus and somehow aligned with the sun. Ordinary explanations are examined in turn. Perhaps the dust production has been unusually strong in the plane of the object's orbit, loading this region with particles that, when seen from Earth, form a sharp edge that looks like a tail. Perhaps the distribution of particle sizes and the timing of ejection conspire to create a narrow band of material that survives for an extended period in the required alignment. However, detailed modeling of dust dynamics under solar gravity and radiation pressure suggests that maintaining such a long, straight, high-contrast structure purely through passive motion is extremely difficult. Larger dust grains that would be less affected by radiation pressure can, in principle, travel further without being pushed strongly away. But they also spread more slowly along the orbit, tending to thicken and blur any initial sharp feature. Smaller grains respond quickly to sunlight and would be diverted into more conventional anti-sunward tails. The antitail of 3I Atlas behaves as if it is supplied continuously and selectively, with conditions that favor a narrow, directed stream back toward the sun. At the same time, spectroscopic data impose an even heavier demand on natural models. When the James Webb Space Telescope disperses the light from the region along the antitail, it does not see only reflected sunlight from dust. It also sees emission signatures from molecules such as carbon dioxide, a volatile gas commonly associated with cometary activity. These signatures can be traced out to distances far beyond the immediate surroundings of the nucleus. In standard cometary physics, gas launched from sublimating ice at a few hundred meters per second cannot continue in a coherent column toward the sun for tens or hundreds of thousands of kilometers. As it moves outward, the expanding gas becomes increasingly dilute, and the solar wind, traveling hundreds of times faster, exerts a ram pressure that quickly halts and then sweeps it back, blending it into the anti-sunward flow. The presence of identifiable gas along the antitail on scales much larger than a few thousand kilometers implies that something is holding or driving this gas against the prevailing flow of the solar environment, or that it is launched with conditions fundamentally different from those predicted by simple sublimation. For researchers accustomed to viewing comets as passive responders to sunlight, this configuration is unsettling. The nucleus of 3I Atlas appears to host an extended, sunward-directed structure, rich in both dust and gas, stable over many days and scales of at least tens of thousands of kilometers, and more prominent than the anti-sunward tail that the solar wind should favor. It is as if the object is projecting material upwind into the stream of solar particles, maintaining a column that pushes back into the incoming flow rather than yielding to it. In fluid terms, it resembles a jet in a river that somehow maintains its shape against the current.
In plasma terms, it suggests an outflow that either begins with much higher speed than ordinary cometary gas, or is supported by forces other than simple thermal expansion and radiation pressure. None of this, on its own, proves that the object is anything other than a highly unusual comet. Yet, the antitail of 3I Atlas stands as a clear, quantitative challenge to the idea that all of its activity can be explained by sunlight gently warming a patchy, icy surface. It is the first large-scale sign that the core assumption behind its classification may be misaligned with reality, that the label Comet rests on ground less firm than the bright, confident images first suggested. Closer to the nucleus of 3I Atlas, where the comet is dense and the structures are more compact, another pattern emerges that deepens the sense that this object is not simply echoing the behavior of familiar comets. When images from the Hubble Space Telescope are processed with specialized rotation gradient filters, subtle variations in brightness sharpen into distinct features. Within a region only a few tens of thousands of kilometers across, 3 narrow jets stand out against the surrounding glow. Each jet is a column of enhanced brightness, tracing material streaming away from the central condensation. One of these jets points roughly opposite the Sun, aligned with the direction that ordinary cometary activity should favor. The other 2 extend from the nucleus in directions that lie to either side, forming a threefold pattern that appears almost evenly spaced around the center. Measurements of their angles on the sky suggest separations close to 1/3 of a full circle between each jet, an arrangement that calls to mind a simple division of space into equal sectors rather than a chaotic scattering of active regions. For observers used to complicated but ultimately irregular jet patterns from comets, this arrangement feels strangely composed. Ordinary comet jets arise from patches of volatile ice on a rotating body. As sunlight warms different regions at different times, some areas respond more vigorously, releasing gas and dust in narrow outflows. The surface of such a body is rugged and varied, shaped by impacts and by countless cycles of heating and cooling. It is natural to expect that active regions would be distributed in a way that reflects this messy history, with no particular preference for equal spacing or clean symmetries. Some comets do show multiple jets that, in projection, fall into patterns that look ordered, but careful studies usually reveal that these are products of viewing geometry, rotation, and chance. The underlying distribution of active areas remains irregular. Against this background, the 3 jets of 3I Atlas appear more disciplined. In enhanced images taken at different dates, the same threefold structure persists, although the exact orientation of the pattern rotates over time. This rotation is consistent with a nucleus spinning around a fixed axis, carrying the jets with it as it turns. Yet, the fact that 3 dominant jets remain spaced at nearly equal angles hints that the surface does not host just any arrangement of volatile patches. It suggests that 3 main sources of activity occupy positions that divide the spin equator, or some other great circle, into nearly equal parts, as if they were placed with an eye towards symmetry. Efforts to reconcile this with simple surface physics begin by imagining a nucleus with 3 major basins or layers enriched in carbon dioxide ice, each separated by similar angular distances. Heating from the Sun could then bring each region into activity as the body rotates, producing jets that emerge in 3 distinct directions. Variations in illumination and local topography might create some differences in brightness and length, but the basic pattern would remain. However, such an arrangement would require either an unlikely accident in the way the nucleus formed, or an unusual history of impacts and thermal evolution that produced 3 large, roughly equal, volatile reservoirs. Simulations of random impact distributions and internal layering rarely yield such tidy outcomes. When scientists map active areas on well-studied comet nuclei, such as the one visited by Rosetta, they find clusters and bands rather than clean partitions. The measured separations between the jets of 3I Atlas, close to 1/3 of a circle each, encourage some researchers to consider whether image processing might be amplifying an apparent symmetry beyond what is physically real. Rotation gradient filters enhance changes in brightness along certain directions. If the underlying coma has subtle variations that align with the chosen processing axes, the output can highlight features that look more structured than the raw data. Teams therefore revisit the original images, test multiple filter orientations, and compare independent reductions. Even under these checks, the triple jet pattern persists. The exact angles shift slightly depending on the method, but the impression of 3 broadly equal spokes anchored to the nucleus remains.
The possibility that artificial intelligence algorithms or automated enhancement tools have invented the pattern is also examined, given the increasing role of such techniques in modern image analysis. Yet, the core features can be recovered with classical, transparent methods that predate such tools, reinforcing the conclusion that the structure is not merely an artifact of software. As the object rotates, the three jets do not simply maintain fixed directions on the sky. Instead, they appear to sweep slowly, as if the entire three-spoke pattern is turning. This behavior fits with a nucleus whose rotation axis is tipped relative to the line of sight. One can imagine a spinning object with three nozzles placed at equal angular separations around its middle. As it turns, each nozzle traces out a cone in space, and an observer watching from a distance sees the projected directions of the jets drift across the sky. In the case of 3I Atlas, the projection produces a pattern that evolves but keeps its internal spacing, a sign that the underlying arrangement on the nucleus remains stable over time. The measured period of this rotation, inferred from changes in brightness and jet orientation, falls near 16 hours, a plausible value for an object of this size. Within such a period, the lengths of the smaller jets can vary by several thousand kilometers as the angle at which they are illuminated and as the local sublimation rate change. Models show that gas launched at a few kilometers per second can build jets of this scale within a single rotation. In that sense, the behavior of the smaller jets is not in conflict with standard comet physics. The deeper tension lies in the combination of this compliant, small-scale behavior with the stubbornly anomalous large-scale antitail and the disciplined threefold symmetry. The minor jets on either side of the anti-sunward direction respond roughly as one would expect from volatile patches on a rotating body. They grow and shrink within reasonable limits, and their speeds are consistent with carbon dioxide-driven sublimation. Yet, their placement at near equal angles around the nucleus aligns them with the base of the larger structures in a way that evokes deliberate design. The jet pointing roughly anti-sunward seems to be the inner root of the more extended anti-sunward tail, a conventional feature. The jet pointing sunward appears to feed the base of the anti-tail, which is profoundly unconventional. The two jets to the sides complete the three-spoke structure, their equal separations lending a sense of simple geometry to the pattern. One astrophysicist, examining this arrangement together with the anti-tail, describes the symmetry as artificial in appearance, not in the sense of being proven technological, but in the sense of resembling what an engineer might choose when designing a stable three-axis system. Three attachment points at equal angular separations provide a natural way to distribute forces or to arrange thrusters, sensors, or funnels for material flow. In many human-built structures, from tripods to certain spacecraft configurations, threefold symmetry offers robustness and balance. The jets of 3I Atlas, only a few tens of thousands of kilometers long near the nucleus, mirror this simple principle on a celestial canvas. To call this pattern artificial in appearance is not to claim that it is artificial in origin. Nature does produce symmetry in many contexts, from crystal lattices to planetary rings. But each time such symmetry appears, it invites a closer look at the underlying processes. Does some natural mechanism select for threefold division in this case? Or is it a coincidence, drawn out of noise by the human tendency to find patterns? As more observations accumulate, the triple jet structure shows no sign of dissolving into the irregularity that might be expected if it were an illusion of sparse data. Instead, it remains a quiet but insistent feature at the heart of the object's activity, pairing with the sunward antitail to suggest that 3I Atlas is governed by a set of organizing principles not yet fully captured by comet models. The inner symmetry echoes through the outer structures, hinting at a connection between the behavior of gas and dust close to the nucleus and the improbable geometry of the large-scale antitail. Somewhere between these scales lies the clue to whether this object can still be called a comet in any meaningful sense, or whether it must be moved into a different, more uncertain category. The persistence of the antitail of 3I Atlas across weeks and across large spatial scales leads naturally to questions about how the nucleus is oriented in space. The rotation of any comet-sized body shapes the way gas and dust are expelled. If a major jet lies close to a rotation pole, it will sweep out a narrow cone rather than a broad band, and its projection on the sky can appear as a stable, elongated feature. In contrast, jets that emerge from regions nearer the equator of a rotating nucleus tend to fan out as the body turns, creating wider structures that change significantly over the course of a single rotation. For 3I Atlas, the antitail is narrow and coherent over distances of at least tens of thousands of kilometers, and perhaps more. This suggests that its source lies near the rotation axis, pointing in a direction that remains almost fixed relative to space, rather than spinning around in a wide circle.
If that axis is itself nearly aligned with the direction of the sun, then a jet emerging from near the pole could naturally aim close to sunward for extended periods, carving a single bright column into the surrounding environment. The image of a lighthouse beam is often used to describe this interplay of rotation and narrow outflow. A light mounted near the pole of a spinning structure sweeps a small circle in the sky. The closer the light is to the exact pole, the smaller the circle. If the light sits exactly on the pole, it does not sweep at all, but instead shines along a fixed direction. By analogy, if the anti-tail of 3I Atlas is the luminous trace of a jet anchored near a rotation pole, then the width of the structure and its degree of wobble provide clues to how closely the axis lines up with the sun. Observations indicate that the anti-tail is at least 10 times longer than it is wide, a ratio that hints at only a small misalignment between the jet direction and the axis. Estimates based on this geometry suggest that the jet deviates by less than about 6 degrees from the spin axis. For such a narrow cone to remain aimed roughly toward the sun over the time span of the observations, the rotation axis itself must therefore lie within a few degrees of the sunward direction. This is not impossible in principle, but it occupies a very small region of the possible orientations a randomly oriented object might have. When researchers calculate the probability that a rotation axis chosen uniformly at random on the celestial sphere would fall within such a small angular distance of the sun, the result is of order a few percent, perhaps around 2%, depending on the precise thresholds used. In other words, if interstellar visitors arrived with all possible orientations equally likely, only a small fraction would present the sort of alignment that 3I Atlas appears to show. On its own, such an unlikely orientation might be dismissed as a simple stroke of happenstance. After all, rare events do occur given enough opportunities, and the solar system hosts many comets whose spin axes take on a broad range of angles. Yet in the case of 3I Atlas, this low probability alignment does not stand alone. It joins a list of other unusual features. The dominance of a sunward-directed anti-tail, rich in gas. The presence of a triple jet structure with near equal angular separations. And the requirement that gas maintain coherence against the solar wind over scales that natural sublimation should not support. Each of these elements adds another layer of tension between ordinary comet physics and the behavior actually seen. The more such conditions are required simultaneously, the less comfortable it becomes to attribute everything to chance, and the more tempting it is to suspect that some underlying organizing principle is at work. Still, responsible evaluation demands that each piece be weighed carefully in physical terms rather than treated purely as a catalog of improbabilities. The inferred rotation period of 3I Atlas, near 16 hours, fits comfortably within the range of known comet spin rates. This period is derived from changing brightness patterns, from the motion of the inner jets, and from the periodic modulation of the coma structure. If the anti-tail jet sits near the rotation pole, its length will not vary dramatically over a single rotation, although minor changes can occur as local conditions on the surface evolve. The side jets, on the other hand, are more sensitive to rotation, and variations of several thousand kilometers across half a rotation are entirely plausible if their gas speeds are around a few kilometers per second. In this sense, the dynamic behavior of the smaller jets does not contradict the idea that they might arise from pockets of volatile ice responding to sunlight. The challenge is not their existence, but their disciplined placement and their relation to the broader anti-tail. To test whether gas dynamics alone could explain the observed structures, researchers construct models that combine rotation, axis orientation, sublimation rates, and the influence of the solar wind. One class of models imagines a nucleus with a rotation axis nearly aimed at the sun, and a dominant polar jet supplied by carbon dioxide sublimation. If the axis alignment is close enough, the polar jet can create a narrow, sunward-directed column. Over time, as the object travels, this jet paints out a path into the incoming solar wind. However, when the speed of the gas is limited to values consistent with thermal escape from sunlight-heated ice, its ability to hold ground against the solar wind is severely restricted. The jet reaches only a few thousand kilometers before the pressure of the incoming plasma flow and radiation forces decelerate and divert it. The structure loses coherence on scales far shorter than those actually observed for the anti-tail of 3I Atlas. To extend the gas significantly farther requires either that the initial speed be much higher, or that additional forces confine and guide the flow. Another class of models examines whether the anti-tail could be composed almost entirely of dust, with the gas confined to regions much closer to the nucleus.
In this scenario, large dust grains, weakly affected by radiation pressure, could remain in a narrow stream along the jet direction, while the spectral signatures of gas far out along the anti-tail might be misinterpreted or contaminated by other effects. Yet, detailed analysis of the spectra, especially those obtained by the James Webb Space Telescope, indicates that carbon dioxide emission is indeed present well beyond the region where simple sublimation models predict significant gas density. The observed extent of molecular tracers into the antitail therefore supports the conclusion that gas, not only dust, occupies large sunward distances, reinforcing the pressure on purely natural explanations. The rotation axis alignment remains a central ingredient in any attempt to preserve the comet hypothesis. Without it, the stability and directionality of the antitail become even harder to account for. With it, some aspects of the geometry gain a foothold in known physics, but the price is an acceptance of a highly specific and improbable orientation for an interstellar object seen only once on its passage through the system. Scientific practice allows such improbabilities when they fit into a broader pattern. No principle forbids rare coincidences. Yet, when such coincidences cluster, they invite deeper scrutiny. Are the symmetric triple jets and the axis alignment with the Sun independent accidents? Or do they share a cause rooted in the interior structure or in some external influence? If there is a natural mechanism that favors such a configuration for interstellar objects, it has yet to be identified in the standard literature on small body dynamics. At this point in the unfolding story, the classification of 3I Atlas as a comet still stands formally, supported by the detection of volatile-driven activity and by the presence of a coma and tails. However, under the surface of official labels, a sense of unease is growing. The rotation axis seems almost too well placed, the jets too evenly spaced, the antitail too persistent and too rich in gas. When astrophysicists describe certain aspects of the structure as artificial in appearance, they are signaling that these configurations resemble the outcomes of design problems they have solved in other contexts, not that they have proven an artificial origin. The interplay of rotation, alignment, and symmetry in 3I Atlas sends subtle echoes of engineered systems into the realm of natural celestial mechanics. Whether those echoes are meaningful or merely suggestive remains an open question, but they ensure that this interstellar visitor will not be remembered as a simple comet that happened to cross the solar system on its way back into the dark. As the observational picture of 3I Atlas becomes clearer, the question shifts from geometry to raw capability. It is no longer enough to say that the object has a fortunate rotation axis or an unusual pattern of jets. The core issue becomes whether sunlight, acting on ice, can, under any plausible conditions, generate the kind of sunward structure that is actually seen. This requires moving from images and alignments into the language of energy, mass flow, and opposing forces. But the core idea remains simple. Gas that leaves an icy surface at a certain speed can only travel so far against a strong headwind before it is stopped and turned back. If the solar wind is that headwind, then there is a limit to how far any natural cometary jet can push gas toward the sun. In a natural comet, the energy source is sunlight. Photons strike the surface, warm it, and provide the heat needed to lift molecules out of the solid state and into gas. For carbon dioxide ice, which sublimates efficiently under solar heating, the typical speeds that molecules reach as they escape are a few hundred meters per second. These speeds are set by the temperature of the surface and the mass of the molecules. Hotter ice produces faster gas, but only within certain bounds. There is no mechanism in this simple picture to accelerate carbon dioxide by hundreds or thousands of kilometers per second, because there is no engine except thermal agitation. Observations of many comets and direct measurements by missions that have flown through cometary Comet confirm that outflow speeds from sublimation lie in this modest range. The solar wind, by contrast, is a stream of charged particles leaving the sun at hundreds of kilometers per second. Its speed can vary with solar activity, but typical values are hundreds of times higher than the speed of cometary gas. In addition to speed, the solar wind carries momentum and exerts a kind of pressure on anything in its path. When a comet coughs out gas, those molecules rush outward from the nucleus until they encounter the oncoming flow of particles from the sun. The two streams interact. At some distance away from the nucleus, the push of the cometary gas and the push of the solar wind reach a balance. This is a standoff region, a boundary beyond which the cometary gas cannot force its way any closer to the sun because the wind is too strong. Inside that region, the gas still rushes outward. Outside it, the solar wind dominates and carries ionized material away into the anti-sunward direction. To estimate where this balance lies for 3I Atlas, astrophysicists begin with numbers derived from observations. Before perihelion, the James Webb Space Telescope measures the rate at which the object loses mass in the form of gas. The data suggest that the comet is shedding carbon dioxide at a rate of order 1 to a few hundred kilograms per second during this phase. As the object passes closest to the Sun, this rate likely increases by a factor of several, perhaps approaching a few hundred kilograms per second. These values are high, but not absurd for an active object under strong solar heating. If 3I Atlas is a natural comet, then this mass loss reflects the sublimation of volatile ice from its surface. The next ingredient in the estimate is the speed of the gas as it leaves the nucleus. For carbon dioxide-driven activity, models and previous measurements from other comets point to outflow speeds of a few hundred meters per second at most. A commonly adopted characteristic value is around 200 meters per second, though the exact number can vary with temperature and surface conditions. Combining these pieces, one can describe the density of gas in the jet as a function of distance from the nucleus. As the gas expands into space, it spreads out, and its density drops roughly in proportion to the square of the distance. Close in, the gas is dense and exerts a strong outward push. Farther out, it thins and becomes easier for the solar wind to overpower. On the other side of the balance lies the solar wind itself, streaming outward from the Sun at speeds of hundreds of kilometers per second. Its density falls with distance from the Sun, but near the orbit of 3I Atlas, the values are well known from decades of in-situ measurements by spacecraft. From these, one can estimate the ram pressure, the effective push that the stream of particles exerts per unit area. The cometary jet meets this head-on, sending its slower gas into a much faster, more tenuous flow, where the momentum carried by the outflow equals the momentum carried by the incoming wind over the same area. The two forces cancel. Beyond that point in the sunward direction, the cometary gas cannot continue to advance. It is halted, compressed, and then swept sideways and back, joining the anti-sunward tail. When the numbers are put together for 3I Atlas, the result is stark. For mass loss rates of a few hundred kilograms per second and outflow speeds of a few hundred meters per second, the standoff distance where cometary gas can no longer resist the solar wind lies at only a few thousand kilometers from the nucleus. Calculations suggest a maximum of order 5,000 kilometers in the sunward direction for the region that can be filled with streaming gas from sublimation before the solar wind takes over. Beyond this, the anti-tail of a natural comet should contain dust grains, but essentially no free gas still moving sunward. Large dust particles, being neutral and relatively massive, can continue to coast in their initial directions much farther, forming extended dust structures that are shaped gradually by gravity and radiation pressure. Gas molecules, especially if ionized, cannot. They are rapidly turned and carried away along field lines embedded in the solar wind. This reasoning leads to a clear, testable prediction. If 3I Atlas is a comet whose anti-tail is driven solely by sublimation of carbon dioxide ice on its surface, then any sunward-directed gas jet should be confined to a core region no more than a few thousand kilometers long. Beyond that, the anti-tail should be effectively gas-free, composed mainly of dust grains. In such a situation, spectra taken far out along the anti-tail should show only reflected sunlight from dust, with little or no emission from gas molecules. The detailed structure of the dust might still be complex, and projection effects might still create a striking anti-tail, but the chemical signatures of active gas would be limited to the inner region near the nucleus. This prediction has deep implications for how one interprets the Hubble images that show the anti-tail of 3I Atlas extending tens or even hundreds of thousands of kilometers toward the Sun. On the scale seen in those images, natural sublimation-powered gas should have long since been halted and redirected. If, despite that, significant gas traces are detected along the anti-tail at these distances, then one of the assumptions going into the calculation must be wrong. Either the gas is somehow launched at speeds far higher than those allowed by thermal sublimation of carbon dioxide ice, or the solar wind is being modified or deflected by some unusual mechanism, or the anti-tail is not being powered purely by simple sunlight on natural ice. It is in this context that Avi Loeb, an astrophysicist with experience in both theoretical modeling and the study of unusual astrophysical phenomena, approaches the problem. Rather than focusing first on geometry or visual impressions, he formulates the question as a matter of physics. What are the maximum gas speeds that can be expected from sunlight-driven sublimation on a body like 3I Atlas? What mass loss rates are consistent with measurements from James Webb? Given those values, how far can gas be expected to travel toward the Sun before the solar wind forces it to turn? The answers converge on the same conclusion. Under the constraints of natural comet behavior, gas should not be streaming sunward beyond a distance of roughly 5,000 kilometers from the nucleus. The antitail, on the scales seen in images, should be a dust phenomenon only. This does not yet say anything about what 3I Atlas truly is.
It simply sets a boundary around what a comet, defined as a body whose activity is powered by sublimation of its own volatile ice under sunlight, can do. Inside that boundary, there is room for a range of behaviors. A comet can be unusually active, can have a sharply collimated jet, can lose mass at rates near the upper end of what is observed in other cases. But the combination of gas speed, mass flow, and solar wind strength sets a hard limit on the sunward reach of that activity. If observations reveal streaming gas well beyond this radius, then by the strict definition used in the physics, the phenomenon is not being driven by ordinary cometary sublimation alone. The object may still contain ice, still form a coma, still grow tails, but the defining process behind its most conspicuous feature would not be the same as in traditional comets. The value of this approach lies in its clarity. It offers a straightforward test. Look far along the antitail of 3I Atlas. Examine the light there. If only dust is present, then the comet hypothesis remains viable, even if strained by geometry and symmetry. If gas is present in significant amounts, far beyond the standoff distance, then sunlight on ice cannot be the sole driver, and a different explanation is needed. The scene is then set for the next stage of the investigation, in which space-based telescopes attempt to trace the chemical signatures of 3I Atlas along the very length of the structure that, under the comet hypothesis, ought to be quiet, empty of active gas, and dominated by the mute reflection of dust alone. The test that the physics demands is simple to state and difficult to ignore. If the antitail of 3I Atlas is driven purely by sunlight lifting carbon dioxide from an icy surface, then gas should not be streaming sunward much beyond a few thousand kilometers from the nucleus. Dust may fill the long, thin spear of light seen in images, but the gas should be confined to an inner core. To see whether this is true, observers turn to the one instrument best suited to trace faint molecules against the dark, the infrared spectrographs of the James Webb Space Telescope. Unlike cameras that record only brightness and shape, these instruments spread light into a rainbow and measure the strength of specific colors associated with particular substances. Carbon dioxide has a distinct pattern in this infrared spectrum, a series of features that stand out when the gas is present. By pointing James Webb along the axis of the antitail and sampling light at different distances from the nucleus, astronomers can ask a direct question. Does the signature of carbon dioxide fade away within a few thousand kilometers, as the comet hypothesis requires, or does it persist much farther out along the sunward column? In the processed data, the answer emerges with unsettling clarity. Emission features associated with carbon dioxide are not confined to the region near the coma. They can be traced outward along the antitail to distances far beyond the 5,000-kilometer standoff scale calculated from simple sublimation models. The exact reach depends on the sensitivity of the observations and the background noise, but the pattern is clear. Wherever the antitail glows as a narrow, coherent spine toward the sun, the spectral fingerprint of carbon dioxide accompanies it. The gas is not a local halo clinging to the nucleus. It is present all along the sunward structure, at distances where the solar wind should long since have halted and repelled any natural sublimation-driven outflow. This single fact, the survival of identifiable gas on scales an order of magnitude larger than allowed by thermal escape speeds, presents a direct contradiction to the picture of 3I Atlas as an ordinary comet. The implications unfold step by step. If carbon dioxide molecules are seen tens of thousands of kilometers upwind of the nucleus, then either they have been launched with speeds far greater than a few hundred meters per second, or they are being continually replenished along the antitail by some process that does not originate only at the surface. The first option would require an energy source more concentrated than sunlight on an icy crust. To accelerate carbon dioxide to several kilometers per second or more demands focused power and a mechanism to convert that power into directed motion, something akin to a rocket engine or an ion drive, rather than a patch of warm ground. The second option, in which gas appears all along the antitail rather than simply streaming from the nucleus, would imply a chain of distributed sources embedded in the structure itself, each adding new material against the flow of the solar wind. Neither scenario fits comfortably within the classical comet framework. In that framework, all volatile material originates in the nucleus and escapes when sunlight reaches it.
There is no provision for energetic nozzles or for extended networks of gas sources stretching out into space. To ensure that no hidden assumption is quietly biasing the interpretation, researchers examine other possible explanations. Could the apparent carbon dioxide signature at large distances be a misreading of the data, perhaps arising from scattered light or from overlapping background sources? Detailed analyses attempt to subtract these contributions, checking whether the signal remains when all known sources of contamination are removed. The persistence of the spectral features along the antitail after such corrections strengthens the conclusion that the gas is genuinely associated with the structure. Another possibility is that the gas is not moving sunward at those distances, but has already been turned by the solar wind, with the observed emission simply lying in projection along the antitail. However, the spatial distribution of the signal, its alignment with the narrow column, and its brightness profile as a function of distance all point to a coherent, directed structure rather than a chance overlay of swept-back gas on a dust spike. The antitail behaves as a single, unified entity, and the gas within it appears to share that cohesion. At this point, the boundary conditions derived in earlier calculations begin to act like a gate. If the antitail contains gas all along its visible length, and if that gas cannot be delivered there by ordinary sublimation pushing against the solar wind, then the system driving the antitail is not a classical cometary engine. By definition, a comet is a body whose characteristic tail is generated by sublimation of its own ices under sunlight. Remove that mechanism as the primary cause, and the label starts to lose meaning. The object may still be small, icy, and active, but the dominant sunward structure is not a comet tail in the traditional sense. It is something else, a jet or shield or plume, powered by a process capable of sustaining gas against the sun's wind over extraordinary distances. Avi Loeb frames this conclusion in careful mathematical terms. Starting from measured mass loss rates and gas speeds, he shows that the sunward reach of sublimation-driven gas is capped at a few thousand kilometers. He then compares this limit with the observed extent of carbon dioxide emission along the antitail. The mismatch is so large that no modest adjustment of parameters can repair it. One cannot simply double the gas speed or triple the mass flow and hope to close the gap. The solar wind is too fast and too persistent, and the scaling of the standoff distance is too unforgiving. To push the boundary out to the observed tens or hundreds of thousands of kilometers, the launch speed of the gas would need to increase by more than an order of magnitude. The required velocities move from a few hundred meters per second into the realm of several kilometers per second or more. Values characteristic not of sublimation, but of engineered propulsion systems. This does not automatically imply that 3I Atlas carries engines. It does, however, strip away the comforting claim that nothing beyond normal comet physics is needed. The data from James Webb act as a kind of forensic trace along the antitail, marking where gas exists and where simple models say it should not. Within that gap between prediction and observation lies the mystery that now defines the object. 3I Atlas is still seen to host a coma, to bear multiple jets, and to ride a hyperbolic path through the solar system. But the feature that most clearly distinguishes it, the sunward antitail rich in carbon dioxide, cannot be reconciled with the behavior of any known natural comet under the same conditions. In response, some researchers advocate caution, urging that all possible natural pathways be explored before invoking exotic explanations. Perhaps the internal structure of 3I Atlas is more complex than assumed, with channels that guide gas along magnetic fields. Or, perhaps unusual interactions with the solar system plasma environment create effective confinement that allows gas to persist farther upwind than simple models suggest. These ideas are speculative in their own way, but they share a desire to keep the phenomenon within the boundaries of astrophysical processes that operate without intent or design. Others argue that, while caution is essential, the role of science is also to follow the implications of data wherever they lead, even if that path passes uncomfortably close to scenarios that resemble technology. What unites both perspectives is recognition that the observation of gas throughout the antitail demands an explanation beyond the standard comet template. Whatever 3I Atlas may ultimately be, it has crossed that line. When the presence of carbon dioxide gas all along the antitail of 3I Atlas becomes difficult to deny, the discussion quietly shifts from details of flow and geometry to the meaning of a single word. For decades, the term comet has carried a specific physical implication. A comet is not only a small icy body that passes through the inner regions of a planetary system. It is a body whose activity is driven primarily by the sublimation of its own volatile ices under the light of the star. The coma, the dust tail, the ion tail, all are understood as downstream consequences of this simple engine. Sunlight warms the surface. Ices vaporize, gas escapes, and dust comes along for the ride. Everything else in the comet narrative builds on that foundation. When the nature of 3I Atlas is first discussed, the label comet is applied because the object appears to follow this script. It brightens as it approaches the sun. It develops a coma. It sprouts jets and tails. Spectra show carbon dioxide and other volatiles in its vicinity. The hyperbolic nature of its trajectory makes it interstellar, but that seems at first to be an additional fact layered on top of the comet identity, rather than a challenge to it. The object is described as an interstellar comet, an outsider that behaves according to rules already known from the home system. Only when the antitail is examined in detail does the core assumption behind this label begin to unravel. The careful calculations that relate gas speed, mass loss rate, and solar wind pressure do not rely on fine-tuning. They simply ask how far gas launched at a few hundred meters per second can push into a headwind that blows hundreds of kilometers per second faster. The answer, a standoff distance of a few thousand kilometers, is robust under a wide range of input values. When observations show carbon dioxide gas far beyond that distance along a clearly sunward column, the conclusion follows as a matter of logic. The defining process that is supposed to power a comet tail, thermal sublimation of ice, cannot be responsible for what is seen. The antitail of 3I Atlas does not behave like a comet tail in the strict physical sense. It is something else, fueled by a source that delivers more directed energy than sunlight on a patch of ice can provide. At first, this conclusion coexists uneasily with the familiar language of cometary science. Papers and reports may still refer to 3I Atlas as a comet out of habit and convenience, while acknowledging that certain features resist explanation. There is a natural reluctance to abandon a classification that ties the object to a well-understood category. Yet the more clearly the mathematical limits are stated, the more difficult it becomes to maintain the old label without qualification. If the behavior that most strongly defines the object is not generated by the standard comet process, then continuing to call it a comet risks hiding the very anomaly that demands attention. In quiet discussions, the question begins to appear in a different form. Is 3I Atlas truly a comet at all? Or is it a different kind of interstellar object that happens to carry ice and dust, but uses them in ways not captured by comet models? The history of astronomy offers many examples of names that have shifted as understanding has deepened. Objects once grouped together are later split into distinct classes when new data reveal important differences. Categories that seemed obvious to the eye turn out to mix phenomena with different origins and mechanisms. Distant worlds that were once counted as planets are later placed in a separate family when their orbits and compositions fail to match the main group. Stars, nebulae, and galaxies have all undergone such reclassification at various times, their labels refined to reflect the physics that governs them. In each case, the change is not merely a matter of vocabulary. It shapes how questions are asked, which comparisons are made, and what theories are considered suitable. In the case of 3I Atlas, the pressure to rethink the label comet does not arise from a preference for novelty, but from a mismatch between definition and observation. If one clings to the classical description, then the gas in the antitail becomes a contradiction that must be explained away. If one instead accepts that an object can have a coma and tails, yet not be a comet in the traditional sense, new possibilities open. The antitail can be treated as a phenomenon in its own right, without the constraint that it must be produced by sublimation alone. This shift in perspective has subtle but far-reaching effects. Once the comet label is set aside, or at least placed in doubt, features that previously looked like unusual variations on a familiar theme begin to stand out as independent clues. The triple jet symmetry no longer needs to be forced into the mold of random active areas on a rough surface. It can be examined as evidence for some organizing structure, whether natural or artificial. The alignment of the rotation axis with the Sun, once framed as an unlikely but tolerable coincidence for a comet, can instead be considered as a potential requirement of whatever system is generating the antitail. The presence of gas at great sunward distances no longer has to be reconciled with low-speed sublimation. It can be read as a sign that some process is accelerating or maintaining gas flow against the solar wind, far beyond the range allowed by passive heating. In this new framing, the question becomes not how an interstellar comet might stretch its natural abilities to match the observations, but what kind of interstellar object could naturally produce such phenomena. This does not mean that exotic or technological explanations suddenly become inevitable. There remains a broad landscape of possibilities within advanced astrophysical processes, including interactions with magnetic fields, unusual plasma environments, or internal energy sources that are not driven by surface sublimation alone. However, it does change the baseline against which speculation is measured. A model that treats 3I Atlas as a specialized plasma structure or as an object with internal power sources is no longer disqualified simply because it does not fit the Comet template. The template itself has been set aside as inadequate. The formal step of declaring that 3I Atlas is not a comet, taken by those who push the implications of the calculations to their logical end, is therefore less dramatic than it might appear. It is not a leap into science fiction, but a natural consequence of obeying the limits imposed by physics. If the defining engine of a comet cannot account for the most prominent feature of the object, then the term comet ceases to be descriptive. The object has to be understood under a different category, even if that category does not yet have a settled name. Perhaps it is best thought of as an interstellar artifact whose surface still contains ice, or as a compact body with attached systems that manipulate gas and dust. Perhaps it is a new kind of naturally powered plasma structure that happens to mimic some aspects of cometary behavior while being driven by processes yet poorly understood. Whichever path one considers, the crucial point is that the language shifts from trying to fit the object into an old box to asking what sort of box might be needed to hold it. In the wider community, responses to this reclassification vary. Some prefer to keep using the term comet with extensive qualifiers, speaking of an interstellar comet with anomalous anti-tail properties while investigations continue. Others adopt more neutral language, referring simply to an interstellar object or to 3I Atlas by name, without attaching a category that implies a mechanism. Underneath this variety, there is a growing recognition that the object occupies an uncomfortable borderland between known kinds of small bodies. It shares superficial traits with comets, but refuses to comply with the physical rules that bind them. It carries the chemical fingerprints of volatile ice, yet channels that ice into a sunward structure that behaves more like a directed system. It spins like a natural fragment, yet arranges its jets in a pattern that recalls engineered symmetry. In this tension between familiar appearance and unfamiliar behavior lies the heart of the mystery. 3I Atlas has ceased to be interesting merely as the third interstellar comet discovered. It has become a test of how flexible scientific classifications can be, and of how open the community is to objects that do not easily fit existing schemes. By pushing against the boundaries of what a comet can be, it forces attention onto deeper questions about what kinds of active systems can exist in space, how they might reveal themselves, and how much of what is seen can be explained by blind physics alone. The scene is now set for more speculative interpretations, grounded not in a desire for drama, but in the hard fact that one of the most basic labels in small-body astronomy no longer applies without strain. 3I Atlas is not a comet in the ordinary sense. Whatever is driving its anti-tail, its triple-jet symmetry, and its aligned rotation, it is something beyond the quiet sublimation of ice under a distant sun. Once the conclusion is drawn that ordinary sublimation cannot be the sole engine behind the anti-tail of 3I Atlas, a new landscape of possibilities opens. In this wider view, the presence of carbon dioxide gas far along a narrow sunward column is not a contradiction to be forced back into the comet framework, but a clue pointing towards some other kind of system. The straightest reading of the data is that gas is being accelerated or maintained against the solar wind over distances that natural cometary processes cannot support. In human experience, the acceleration of gas to high, directed speeds is the province of propulsion devices and plasma systems. That analogy does not. In this view, carbon dioxide is not merely frozen material baked off an ancient surface, but a working fluid chosen for its properties in a propulsion system. On Earth, research has explored the use of carbon dioxide as part of multi-component propellant mixtures in ion and Hall effect thrusters. These devices ionize gas, turning it into a plasma of charged particles, and then accelerate that plasma through electric or magnetic fields to speeds far exceeding those of thermal sublimation. Where sunlight on ice can launch molecules at a few hundred meters per second, ion thrusters routinely reach exhaust speeds of tens of kilometers per second. At such speeds, a gas jet could, in principle, carve out a path against the solar wind over much greater distances before being turned. A column of high-speed plasma aimed sunward from 3I Atlas would encounter the solar wind not as an overwhelming force, but as a counterflow that could be balanced or even pushed back locally. In this speculative picture, the anti-tail becomes the visible trace of propulsion, a constant plume of exhausted ions streaming upwind. The triple-jet symmetry near the nucleus could then represent three main thruster clusters, arranged at equal angular separations for stability and control. One cluster would point roughly sunward, producing the anti-tail. Another would point roughly anti-sunward, contributing to the conventional tail. The remaining jets could serve for lateral control or for other functions, their equal spacing providing a balanced platform. The rotation axis would naturally align close to the direction in which sustained thrust is applied, a configuration that minimizes unwanted torques. This arrangement would make the observed alignment between the spin axis and the Sun a consequence of the thrust geometry rather than a random coincidence.
In such a scenario, the gas seen along the antitail is not limited by the energy of sunlight on ice, but by the power of an internal system capable of sustaining ion flows at many kilometers per second. The presence of carbon dioxide in the exhaust would then be a sign of the chosen propellant mixture, rather than a direct clue to the composition of the original body. The standoff distance that constrains sublimation-driven gas would no longer apply in the same way, because the launching speeds and densities would be set by engineering choices rather than by surface temperature alone. However, this picture, while consistent with certain aspects of the data, also raises questions. What source of energy drives these hypothetical thrusters? How is carbon dioxide supplied and ionized in the quantities implied by the observed mass loss rates? Why would an interstellar craft or artifact choose to thrust directly against the solar wind in such a conspicuous way, rather than orient its engines differently? These questions do not invalidate the idea, but they emphasize that technological explanations cannot simply be pasted over the anomaly. They must themselves be coherent systems. Another family of ideas treats the antitail not as exhaust, but as a shield. The solar wind is a flow of charged particles that can damage electronics, erode surfaces, and pose hazards to biological organisms. In human spaceflight, strategies have been proposed to protect spacecraft and habitats using artificially generated plasma structures. One concept involves creating a bubble of ionized gas around a craft, maintained by magnetic fields and plasma injection that deflects incoming solar particles. Another involves deploying extended plasma sails, or shields, that stand between the object and the Sun, intercepting and diverting the wind. In this context, the antitail of 3I Atlas could be interpreted as a kind of plasma curtain erected sunward, a region rich in charged carbon dioxide that interacts with incoming protons and electrons, slowing them and diverting their paths. The narrowness and length of the antitail would then reflect a deliberate attempt to maximize shielding in the direction of greatest exposure. The triple jet symmetry might mark the anchor points of such a system, with 3 main injection regions feeding the extended shield. The rotation axis alignment would again serve a functional purpose, keeping the shield oriented toward the Sun as the object travels. If this picture is correct, then the gas in the antitail does not simply push against the solar wind in a mechanical way. Instead, it forms a medium in which electromagnetic forces can be manipulated. Charged particles entering the shield could be deflected through interactions with the plasma and with magnetic fields generated by currents in that plasma. The same physics explored in magneto-hydrodynamic propulsion and plasma confinement on Earth would operate here on a vast, tenuous scale. The standoff distance derived for neutral gas launched by sublimation would no longer represent a hard boundary, because the shield would involve an active feedback between the injected plasma and the solar wind, possibly sustaining a structure that extends far beyond the reach of passive outgassing. Spectral signatures of carbon dioxide along the antitail would then be the byproduct of this shielding system, a trace of the ions used as the working medium. A variant of this idea imagines the antitail not only as a defensive curtain, but as an energy collection system. The solar wind carries kinetic energy in its swift particles and electromagnetic energy in its embedded magnetic fields. Some speculative concepts in human space engineering have considered the possibility of harvesting this energy using large fields or sails that couple to the plasma flow. In the context of 3I Atlas, the dust, or apparent dust, in the antitail could be a swarm of small devices, perhaps nanometer or micrometer scale machines, designed to intercept solar wind particles and extract energy from them. After harvesting this energy, these units could ride the anti-sunward flow back toward the nucleus or some collection region, either physically returning or transmitting energy via radiation. The observed antitail would then be the visible footprint of an enormous dynamic system for interacting with the star's outflow. In this scenario, the presence of carbon dioxide gas might arise from the operation of these devices, from cooling flows, or from some interaction between the swarm and residual volatiles on the parent body. Such ideas move far beyond the comfort zone of standard astrophysics and enter a region where technology is invoked at scales and levels of advancement that are difficult to test directly. For this reason, many researchers approach them with caution. At the same time, the logic that drove the rejection of the pure comet hypothesis also demands honesty about what kinds of processes can, in principle, match the observations.
Systems that deliberately accelerate gas or manipulate plasma are among the few known ways to maintain coherent structures against the solar wind over great distances. If 3I Atlas is not such a system, then some natural mechanism with similar capabilities must be found.
Between the clear limits of sublimation and the unknown territory of advanced technology lies a gray zone of exotic but possibly natural plasma phenomena. One could imagine, for example, that 3I Atlas carries a strong, ordered magnetic field, perhaps inherited from its origin environment, that shapes the flow of gas in ways not captured by simple models. Gas leaving the nucleus could be guided along field lines into a narrow column, and interactions with the solar wind could produce standing structures that maintain coherence over long distances. In such a case, the language of engines and shields might still be useful metaphorically, even if no deliberate design is involved. Nature sometimes builds systems that behave like machines without having been built as machines in any intentional sense. The challenge is to articulate a specific natural pathway that leads to such an arrangement under realistic conditions, something that has not yet been achieved in published models. Each of these scenarios, whether technological or natural, must account for certain non-negotiable facts. The antitail contains carbon dioxide gas over distances much larger than allowed by thermal sublimation alone. The structure is narrow, coherent, and aligned roughly sunward. The inner jets are arranged with near equal angular separation around the nucleus. The rotation axis appears closely aligned with the Sun. Any proposed mechanism must make these features probable outcomes rather than arbitrary coincidences. A propulsion system with symmetric thrusters and a preferred thrust direction naturally does this. A shielding system that must face the Sun does so as well. A swarm-based energy collector anchored in 3 main injection regions could also fit. A natural plasma structure would need some reason to favor threefold symmetry and axial alignment. As long as that reason remains unspecified, the natural side of the ledger feels incomplete. For now, the engines, shields, and swarm concepts remain in the realm of informed speculation. They offer frameworks in which the observed phenomena can be understood as expressions of active control over gas and plasma, rather than as passive responses to sunlight. They are anchored to real technologies and physical principles studied on Earth, but they extend those principles to scales and contexts far beyond human engineering. Whether 3I Atlas truly embodies any of these ideas is unknown. What is clear is that the object has forced consideration of such possibilities out of the domain of pure imagination and into the edges of scientific discourse. Not because of a desire for sensational conclusions, but because the data have removed the simplest natural explanation from the table. As 3I Atlas recedes from the inner solar system, climbing back toward the dark between the stars on its open path, the possibility of ever knowing its true nature begins to narrow. The object is not bound to the Sun. It passes through once, leaving a brief trail of data, and then continues outward, its distance growing, its brightness fading. Telescopes that once captured detailed images of its coma and antitail now struggle for photons. Integration times lengthen, the signal drops toward the background. The most dramatic phase of its activity lies behind it, recorded in the archives of observatories on Earth and in space. The story of the antitail, of gas where gas should not be, now shifts from active observation to careful analysis, and to the question of what, if anything, can still be done while the object remains within reach of instruments. Even in this fading phase, there are opportunities. Space-based observatories can be scheduled for additional pointings, aimed not at the bright, sharp structures of earlier months, but at the lingering traces in the region where the antitail once blazed. By taking spectra at different times and distances as the object moves outward, scientists can watch how the signatures of carbon dioxide and other molecules change. If the gas in the antitail is a one-time outburst, its marks may fade quickly once the putative engine or shield is turned off. If it is part of a more persistent system, the decline may follow a different pattern. Comparing these decay curves to those of ordinary comets can provide further clues. Ground-based telescopes, equipped with sensitive spectrographs and adaptive optics, continue to sweep the region, catching any residual structure in the dust and plasma. Radio observatories listen for emissions from molecules that radiate in longer wavelengths, tracing motion in another domain. Each fragment of data, even as the signal weakens, helps refine models and tests earlier assumptions. At the same time, the idea of sending a spacecraft to intercept 3I Atlas arises almost inevitably. The interstellar visitor presents a unique opportunity. A probe equipped with cameras, spectrometers, and particle detectors could fly through the antitail region, sampling gas and dust directly.
measuring fields and flows, and perhaps even imaging the nucleus up close. Such a mission would turn speculation into direct inquiry. However, the practical constraints are severe. Interstellar objects like 3I Atlas move quickly relative to Earth, and they are typically discovered only after they have already entered the inner solar system. Designing, building, and launching a dedicated mission in the short window before the object recedes beyond reach is a challenge that current space agencies are not fully prepared to meet on short notice. Studies of rapid response missions exist in concept form, but the infrastructure for immediate execution is not yet in place. For 3I Atlas, by the time its most intriguing features are recognized and the full weight of their implications is appreciated, the object is already outbound, too far and too fast for anything other than speculative trajectories on paper. The chance for an in-situ investigation passes silently, marked only by the recognition that such opportunities may come again, and that next time, preparation will matter. This recognition leads to a different kind of response. If 3I Atlas cannot be pursued, future interstellar visitors can be anticipated. The data it leaves behind become a template for what to look for next time. Automated search pipelines that comb through survey images can be updated to flag not only hyperbolic trajectories, but also unusual tail geometries and spectral signatures. Alert systems that inform observatories of new arrivals can be tuned to trigger more quickly, reserving time on space telescopes earlier in the passage. Mission concepts for rapid response probes can be refined, with designs that sit in waiting, ready to be launched on short notice when a sufficiently intriguing target appears. 3I Atlas, by revealing how surprising an interstellar object can be, pushes the community to think more systematically about how to study the next one. Meanwhile, the analysis of existing data continues to deepen. Simulations grow more sophisticated, incorporating realistic solar wind variations, three-dimensional plasma flows, and complex magnetic field structures. Modelers attempt to reproduce the anti-tail and triple jet behavior without invoking any form of technology, exploring whether exotic but natural plasma processes around a magnetized body could produce similar features. They test scenarios in which the nucleus holds a remnant field that guides gas into narrow streams, or in which interactions between the outflow and the heliospheric environment generate standing waves. These models occasionally produce structures that mimic parts of the observed configuration, but none yet reproduce the full combination of long-range gas, sunward alignment, and threefold symmetry in a robust way. Each failure is instructive, illuminating which physical mechanisms are insufficient on their own and which need to be combined. The aim is not to force a natural solution, but to map out the space of what physics, unaided by intent, can plausibly achieve. On the speculative side, others continue to explore the technological interpretations, not as conclusions but as structured hypotheses. In this mode of thinking, 3I Atlas becomes a case study in what a large-scale plasma system or propulsion network around an interstellar artifact might look like from afar. Researchers consider how often such objects would be detectable, how their signatures might vary with orientation and activity level, and how to distinguish them from rare natural phenomena. They examine whether the energetics implied by the anti-tail are consistent with known forms of power generation, scaled up to astronomical levels, and whether any leakage in the form of radio or other emissions might be detectable. In this sense, 3I Atlas merges with broader efforts to search for technosignatures, signals from technology beyond Earth, not through the traditional channel of radio beacons, but through dynamical and morphological anomalies in small bodies and circumstellar material. The object becomes a prompt to widen the definition of what a technological footprint in space might be. In academic seminars and informal discussions, 3I Atlas occupies an ambiguous place. It is presented alongside other interstellar visitors as a member of a tiny but growing family. Yet, its anti-tail and jet structure set it apart. It is referenced in debates about how to weigh unlikely alignments and patterns, about the balance between caution and openness in interpreting anomalies. Some argue that the object should be treated as a natural phenomenon until a clear, testable prediction from a technological model is met, perhaps by a future observation of another object with similar features. Others hold that the failure of standard comet physics to account for the anti-tail justifies keeping technological explanations in active consideration, even if they remain speculative. Both sides agree that more data, from this object or from future ones, will ultimately be needed to break the stalemate. For the broader field of planetary science and astrophysics, 3I Atlas serves as a reminder that categories and expectations, however well supported, are provisional. Before its arrival, comets were assumed to be governed by a small set of processes well captured by existing models.
Interstellar comets were expected to add variety, but not new rules. The behavior of this object calls that assumption into question. It shows that small bodies arriving from other systems can bring with them dynamics that strain local frameworks. And it hints that the diversity of such visitors may be far greater than the few examples so far suggest. In this way, 3I Atlas acts as both a specific mystery and a general warning against overconfidence. As the object fades into the distance, its observational footprint becomes fixed. No new images of the dramatic antitail will be taken. No spacecraft will swing past to send back close-ups of the nucleus. What remains are the records, the Hubble frames with their 3 jets and sunward plume, the James Webb spectra with their carbon dioxide signatures far upwind, the timing and geometry of the rotation, the hyperbolic path out of the planetary system. These are now part of the enduring dataset of astronomy, available for reanalysis with new tools and new theories. Future generations may revisit them with techniques and frameworks not yet imagined, perhaps seeing patterns that current thinking obscures, or confirming suspicions that now must remain tentative. In the present, 3I Atlas hovers in a state of unresolved identity. It has been shown not to be a comet in the strict process-based sense. It has been suggested as a candidate for advanced plasma phenomena, or as a possible technological artifact, but no decisive evidence exists to fix it in any of these roles. It is an interstellar object that has crossed the solar system, leaving behind a set of anomalies that do not yet assemble into a single, satisfying picture. Its antitail remains a narrow, bright question, pointing back toward the sun. Its triple jets an echo of some organizing principle at work on scales both small and large. The object recedes, but the puzzle it has written into the sky persists, inviting continued effort and reminding those who study it that the universe still has ways of surprising even well-prepared minds.